In this video, we're going to introduce the concept of a limit. In calculus, everything that we learn in calculus is based on the idea of a limit. Not only are limits important, but they underline the two fundamental operations in calculus, differentiation and integration. So limits are a big concept in calculus. We're not going to get into the algebraic definition and manipulation of a limit, but we are going to look at understanding what a limit is graphically. So first, let's talk about what a limit is. As x approaches some value a, so if we're thinking about x along the horizontal axis, as we're approaching some value a, the limit of a function is some value L. This is the value that the function approaches, thinking about the y value. So our limit is, the output of a limit is a y value. Now, it's important to note that a function doesn't have to be defined at that value of x for the limit to exist. And the notation for a limit is the limit as x approaches a of f of x is equal to L. Now we also have one-sided limits. So what we were just referring to, generically the limit, we are thinking about approaching that value of a from both sides, from the left and from the right. A one-sided limit allows us to approach some value of a from the left or the right side. So if we're approaching some value a from the right or the positive side, the limit of a function a is L. Or the limit of a function is the value L. This is the y value that the function approaches from the right side. Again, the function doesn't have to be defined at x equals a for that one-sided limit to exist. In terms of our notation, we denote that we're looking at a right-sided limit by adding a plus sign in that x approaches a plus notation. Similarly, a left-sided limit, we're looking at what the function is approaching as x approaches a from the left, or that negative side. Function does not need to be defined at a for that one-sided limit to exist, and the change in our notation, instead of having that plus, we have a minus sign on x approaches a. So x approaches a with a superscript of negative or a minus sign is that left-sided limit. Now that first limit that we discussed, the general idea of a limit, only exists if the limit from the left and the limit from the right are the same. So let's look at some of these ideas with some graphs. All right, so we have our graph here, and we're going to answer some questions just looking at the graph. First, what is f of 2? Well, if you look at this squiggly line, here's x equals 2. That squiggly line has a hole where x equals 2, but there's a point at 2, 0. So that tells me that f of 2 is 0, even though the line is not going through that point. The limit as x approaches 2 from the right of f of x, so thinking about coming to 2 from the right, and I'll trace this. So if I'm approaching 2 from the right, it's approaching a y value of -2. Our function's approaching -2. If I think about, the next one should be the limit as x approaches 2 from the left, so that should be a minus, not a plus. Looking at approaching x equals 2 from the left, so now I'm tracing this in yellow. I'm coming from the left side to 2. That's also approaching the value -2, which tells me that the limit as x approaches 2 is -2. Notice the difference. Our function is defined at 2 to be 0, but the limit is -2. So we kept on emphasizing a function doesn't need to be defined at a certain point in order for that limit to exist. It also doesn't have to match. Okay, let's look at another example. Another funky looking piecewise function here. And I believe there's some typos here in these one-sided limits, so we'll correct them as we get there. First, f of 2, looking at the graph, f of 2 is there at 1. As I'm approaching 2 from the right, So coming in from the right, my function is approaching -1. So my limit as x approaches 2 from the right is -1. Now let's look at approaching 2 from the left. Approaching 2 from the left, there's just that little segment, but it looks like it's also approaching -1. So the limit as x approaches 2 is -1. Okay, let's look at f of 6. F of 6, looking at our graph, we're gonna have to approximate that. Let's call it -4.8. Any approximation is fine here. Approaching the limit as x approaches 6 from the right. Well, that's going to be -4.8. The limit as x approaches 6 from the left, also approaching -4.8. So the limit as x approaches 6 is -4.8. Let's identify f of -6. Well, f of -6, since we have open circles on both of those points at x equals -6, that tells me that it's undefined at -6. Our function is undefined at -6. If I'm approaching x equals -6 from the right, then my function is approaching 4. So the limit as x approaches -6 from the right of f of x is +4. If I look at the limit from the left, my function is approaching -1. So the limit as x approaches -6 from the left of f of x is -1. Since the limit from the left does not equal the limit from the right, then the limit as x approaches -6 of my function does not exist. And cue all of the Mean Girl internal quotes, the limit does not exist. Next, we're going to look at infinite limits and limits at infinity. Infinite limits are a limit that is, in fact, infinity. So sometimes a function will grow without bound in either a positive or a negative direction. When this happens, we have an infinite limit. If, as x approaches a from both sides, the function goes up to positive infinity, we say that the limit as x approaches a of f of x is positive infinity. If, as x approaches a from both sides, the function goes down to negative infinity, we say the limit as x approaches a of f of x equals negative infinity. If the function goes to positive infinity from one side and negative infinity from the other side, we say that the limit as x approaches a of f of x does not exist. Again, that is the same idea that we were looking at in that last example, where the limit from the left does not equal the limit from the right, then the limit does not exist. In each case, doesn't matter which of these cases, even if the limit does not exist, these infinite limits are implying a vertical asymptote at x equals a, or indicating a vertical asymptote at x equals a. Now, limits at infinity, this is where we're talking about the limit as x is approaching positive or negative infinity. And a limit at infinity is describing a horizontal asymptote. So if the limit as x approaches positive infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L, then there is a horizontal asymptote at y equals L. All right, so here we have another piecewise function. The limit as x approaches infinity, so we're looking at what's happening with that right tail. Now, this isn't a great picture, but you should be able to tell that it does look like it's coming down and it's approaching that x-axis so that limit as x approaches infinity of f of x is 0. Likewise, if we look at the limit as x approaches negative infinity, that's that left tail, we can see it's starting to get closer and closer to that x-axis. So the limit as x approaches negative infinity of f of x is 0. This is telling me that the horizontal asymptote of this graph is at y equals 0. Now, what's unique about horizontal asymptotes, if you recall from a college algebra course, we can, or a function can cross a horizontal asymptote. We see it happening twice in this graph. And that's because a horizontal asymptote really is just defining the end behavior of your graph. So what's happening as we approach positive infinity and negative infinity on that x-axis. The limit as x approaches -1 from the left. So finding x equals -1 and approaching it from the left looks like it's going up to positive infinity. The limit as x approaches -1 from the right of f of x. Well, that's going down to negative infinity. This tells me that we have a vertical asymptote, even though the limit doesn't exist here because we're approaching different sides, or approaching positive infinity and negative infinity. We still have a vertical asymptote at x equals -1 because of that limit or that infinite limit.